There was a time when the universe was utterly dark, a silent, endless expanse with no stars, no galaxies, just an ocean of nothingness stretching across infinity. Then something extraordinary happened. The darkness shattered. The first stars ignited, flooding the cosmos with light for the very first time, and in that moment, the universe as we know it was born. This is the cosmic dawn era, one of the most mysterious and awe-inspiring chapters in the story of everything. And yet, despite its immense importance, this era remains shrouded in secrets. How did those first stars form? What strange galaxies flickered to life in that primordial darkness? And what unseen forces shaped the universe into what it is today? Right now, we're standing on the edge of discovery, peering back through time and space to unravel these cosmic enigmas. Scientists have spent decades piecing together clues, whispers from the earliest light, echoes from the birth of galaxies, and faint signals from a time when the universe was still in its infancy. But for every answer, there are new questions, deeper mysteries lurking in the shadows of the cosmic dawn, and that's what makes this journey so thrilling. Because hidden within these 25 profound mysteries are the keys to understanding not just our cosmic origins, but our place in the universe itself. This is more than just a story about stars and galaxies. It's a tale of cosmic alchemy, of how emptiness became light, how chaos gave way to structure, and how the universe transformed itself from a featureless void into the breathtaking tapestry we see today. And as we explore these mysteries together, you'll begin to see the universe in a whole new way. Every question we uncover will pull you deeper into the wonder of it all, every revelation more astonishing than the last. So let's begin, not just as observers but as explorers, stepping into the unknown to uncover the secrets of the cosmic dawn. The universe is waiting. Imagine a star unlike anything in our night sky, a behemoth of pure hydrogen and helium, blazing with such ferocity that it could outshine entire galaxies. These were the first stars of the cosmos, known as population 3 stars, and they hold the answer to one of the greatest mysteries of the cosmic dawn. Born from the raw ingredients of the early universe, they were giants hundreds of times more massive than our sun, burning hotter and dying younger than any star we've ever seen. Yet despite their colossal presence, we've never caught a single glimpse of them, not one. The reason? These stellar pioneers lived fast and died violently, exploding in titanic supernova that scattered the first heavy elements across space, seeding the universe for generations of stars to come. By the time light from even the nearest galaxies reaches us, their signatures have faded into the cosmic background. But if we can't see them, how do we know they existed at all? The clues are written in the oldest light. We can detect the faint afterglow of the Big Bang, and the chemical fingerprints left behind in ancient stars that formed from the ashes of those first explosions. Theories suggest these primordial stars didn't form the way modern stars do. Without dust or heavier elements to cool collapsing gas clouds, they may have grown unimaginably massive before igniting, their sheer size dictating their fate. Some might have collapsed directly into black holes, vanishing without a trace. Others could have detonated in supernova on steroids, releasing enough energy to briefly outshine the entire universe. But here's the twist: if even a handful survived longer than expected, hiding in the farthest reaches of space, their light could still be traveling toward us, waiting to be discovered in the next breakthrough observation. The hunt for these ghostly giants is pushing telescopes to their limits, probing deeper into the infrared spectrum where their faint glow might still linger. Every new simulation, every fresh analysis of distant quasar light brings us closer to spotting their shadows in the data. And if we do, it would be like uncovering the very first page of the universe's diary, a story written in starlight before time itself had fully taken shape. Picture this: a universe still cloaked in fog, where light struggles to travel more than a stone's throw before being swallowed by dense clouds of hydrogen gas. Then, in a cosmic blink, everything changes. The fog lifts, light breaks free, streaming unimpeded across space for the first time. This monumental shift, known as reionization, marks the moment the universe became transparent. But here's the puzzle. We still don't know exactly what caused it. For decades, astronomers assumed the first stars were the heroes of this story. Their searing ultraviolet radiation, theorists argued, blasted apart the hydrogen fog like sunlight burning off morning mist. But when researchers crunched the numbers, something didn't add up. There's a glaring gap in the timeline, a period when the stars we've detected simply couldn't have produced enough energy to finish the job. So if stars didn't fully clear the cosmic haze, what did? Enter black holes. Not the quiet, solitary giants we see today, but voracious primordial monsters lurking in the cores of the earliest galaxies. These ancient behemoths, feasting on gas at unbelievable rates, would have unleashed torrents of high-energy radiation far more efficient at ionizing hydrogen than starlight alone. Recent observations of distant quasars support this idea, showing telltale bubbles of ionized gas around early supermassive black holes, yet even this explanation has holes. Some regions of the early universe reionized faster than black hole models can explain, leaving scientists staring at contradictory evidence. The truth might lie in a cosmic collaboration. Perhaps stars lit the first sparks, with black holes amplifying their effect. Or maybe an entirely different player was involved, exotic particles from decaying dark matter, or even outbursts from a population of stars so strange we've yet to imagine them. Each possibility rewrites our understanding of how light conquered the darkness. What makes this mystery so tantalizing is that we're literally seeing its aftermath. The very light reaching our telescopes today has traveled through this partly ionized medium for billions of years, carrying subtle distortions that act like fingerprints of the process. Decoding those signals could reveal whether the universe flickered to clarity unevenly, in patches, or all at once in a brilliant flash. And hidden within that answer is something even more profound, a clue about how the building blocks of the cosmos itself came to be arranged just so, making our existence possible. The hunt for reionization's missing link is pushing astronomers to new extremes. They're scouring the infrared sky for faint galaxies that might tip the scales, building simulations that recreate the universe's childhood down to the quantum level, and waiting for next-generation telescopes to catch whispers from this epoch in radio waves frozen in time. One thing's certain, when we finally piece together this chapter, it won't just fill a gap in our knowledge, it'll rewrite the story of how light shaped everything we see. Deep in the heart of the cosmic dawn, an invisible force was at work, one so powerful it sculpted the universe itself, yet so elusive we've never directly seen it. This is dark matter, the universe's hidden architect, and without it, the first stars and galaxies might never have formed at all. Here's the mystery. While we know dark matter's gravity drew the cosmic gas together, kickstarting the birth of everything we see, its exact role in those early moments remains one of the most heated debates in astrophysics. Think of dark matter like the scaffolding of the cosmos. Ordinary matter, the stuff of stars, planets, and you, makes up less than 5% of the universe's total content. Dark matter outweighs it 5 to 1, its gravitational pull acting as an unseen hand, guiding gas into dense clumps where the first galaxies could ignite. But here's where things get strange. Simulations of the early universe show dark matter should have clustered into smooth, spherical halos around these infant galaxies. Yet when astronomers study the oldest light in the universe, the cosmic microwave background, they find hints that dark matter might have been more lumpy than expected, gathering in unpredictable ways that don't match our models. What could explain this mismatch? One tantalizing theory suggests dark matter wasn't entirely dark after all. A fraction might have interacted with itself or ordinary matter through some unknown force, creating friction that altered how it flowed through space. Imagine stirring honey versus water. The resistance changes how the liquid moves. If dark matter had even a slight drag, it could explain why some ancient galaxies formed faster than simulations predict, or why we see ghostly streams of stars in today's universe that seem to trace forgotten paths of dark matter's dance. Then there's the puzzle of the missing small galaxies. The most accepted model, called cold dark matter, predicts thousands of tiny satellite galaxies orbiting large ones like the Milky Way. But we've only found a few dozen. Some researchers argue this means dark matter was warmer in the early universe, moving too fast to clump into as many small structures. Others propose these dwarf galaxies did form but were too faint to detect, their stars snuffed out by the harsh radiation of the cosmic dawn. The stakes couldn't be higher. Dark matter doesn't just shape galaxies, it dictates the universe's very structure. If its properties were slightly different, stars might have formed too late or not at all. Yet every new discovery seems to deepen the mystery. Recent observations of bizarre, ultra-diffuse galaxies, clouds of stars so wispy they're almost invisible, suggest dark matter might be spread more unevenly than we thought. Meanwhile, cutting-edge experiments are hunting for hypothetical dark matter particles, from actions to WIMP, any of which could rewrite the rules. The irony. We're literally made of the universe's afterthought, the ordinary matter that merely speckles the vast dark scaffold. And as we peer back toward the cosmic dawn, we're not just searching for answers about dark matter, we're uncovering the hidden blueprint of existence itself. One day, solving this shadowy puzzle might reveal not just how the first galaxies lit up, but why the cosmos took the shape it did, making our own story possible. In 2018, a radio antenna in the Australian outback picked up something impossible, a signal from the dawn of time itself. The experiment to detect the global epoch of reionization signature, or edges, captured a faint but unmistakable dip in the 21-centimeter wavelength, a fingerprint of hydrogen gas from when the universe was only 180 million years old. But this wasn't just any signal. It was twice as strong as theorists had predicted, plunging science into one of the most baffling mysteries of the cosmic dawn. What could have made the primordial hydrogen so cold so quickly? The 21-centimeter signal is cosmic archaeology. It works like this. In the early universe, neutral hydrogen atoms absorbed and emitted radio waves at this specific wavelength, leaving a ghostly imprint we can still detect today. The depth of the dip tells us how cold the gas was, while its shape reveals when the first starlight began heating the cosmos. But the edge's data defied expectations. The hydrogen appeared far colder than models allowed, as if something had sucked the heat out of the universe before stars could warm it. One radical explanation involves dark matter. If certain hypothetical particles like weakly interacting massive particles, or WIMP, collided with hydrogen in those early epochs, they could have acted like a cosmic refrigerant, cooling the gas far faster than starlight alone. The numbers are tantalizingly close to fitting, but there's a catch. This would require dark matter to interact with ordinary matter in ways that break every current theory. Some physicists have proposed tweaks like millicharged dark matter with a fractional electric charge, but these ideas remain highly controversial. Then there's the star problem. The timing of the signal suggests the first stars might have flickered on earlier than we thought, their ultraviolet light already bathing the hydrogen by this point. But if that's true, why haven't we spotted these pioneer galaxies yet? Our telescopes should, in theory, be sensitive enough to catch at least a few. Unless, and here's where it gets wild, those early stars weren't like anything we've seen since. Some theorists speculate they formed in dense, dark matter-rich environments, burning differently or fading too fast for current instruments to detect. Others wonder if the signal isn't from stars at all, but from an exotic process we haven't even imagined, like primordial black holes evaporating or quantum bubbles popping in the fabric of space-time. Skeptics argue the signal might be an illusion, a trick of radio interference from Earth, or an error in calibration. But after years of scrutiny, the JWST team stands by their data, and independent groups are racing to confirm it with new experiments. Meanwhile, theorists are rewriting whole chapters of cosmic history to account for this anomaly. If the signal is real, it implies the universe's infancy was stranger, darker, and more dramatic than we ever dreamed. Right now, this mystery hangs in limbo, a single data point challenging our entire understanding of the cosmic dawn. But hidden within that uncertainty is something electrifying, the chance to rewrite physics itself. Because if the JWST signal holds up, we might not just be looking at the fingerprints of the first stars. We could be glimpsing the shadow of dark matter for the very first time. At the heart of nearly every galaxy we see today sits an unfathomably dense monster, a supermassive black hole weighing millions or even billions of times more than our Sun. These cosmic behemoths are so colossal, their gravity bends the very fabric of space around them. But here's what truly boggles the mind. Some of them existed when the universe was less than 1 billion years old. How did they grow so massive, so fast? This isn't just a mystery, it's a cosmic race against time where the rules of physics seem stretched to their breaking point. Take the current record holder, a quasar called J0313-4356. This dazzling beacon of light, powered by a supermassive black hole, existed when the universe was a mere 670 million years old. Yet its black hole already weighed over 1 billion suns. To reach that size in such a short span, it would have needed to devour gas at the maximum possible rate for its entire existence, like a newborn baby growing into a blue whale in just a few months. The math simply doesn't add up. Scientists have wrestled with two main theories to explain this impossible growth. The first suggests these black holes started as massive seeds collapsing directly from vast clouds of primordial gas in the early universe. Picture a cosmic shortcut. Instead of forming from a single dead star, a gargantuan gas cloud hundreds of thousands of times heavier than our Sun could have imploded all at once, skipping straight to a heavyweight black hole. These seeds would have had a head start, gorging on surrounding matter far faster than their smaller counterparts. But there's a twist. Simulations show these gas collapses needed near-perfect conditions, clouds that stayed cold, undisturbed, and free from disruptive starlight. Even a single massive star forming nearby could have blown the gas apart before it collapsed. That's led some researchers to an even wilder idea. What if supermassive black holes weren't born from gas at all, but from something far stranger lurking in the universe's first moments? This is where primordial black holes enter the story. Unlike stellar black holes formed by dying stars, these could have been forged in the seething chaos just after the Big Bang, when quantum fluctuations packed dense pockets of matter into instant black holes. Some might have been as small as an atom, while others could have weighed thousands of suns right out of the gate. Over time, the largest ones would have sunk into the centers of young galaxies, feeding greedily on the surrounding gas. It's a compelling idea, except we've never found direct evidence these primordial black holes exist. The debate gets even murkier when you consider how these black holes fed. Modern supermassive black holes often flicker between feast and famine, their growth limited by the intense radiation they emit while eating. But recent simulations suggest early black holes might have found a loophole, feasting in dense, dark matter-rich halos where gas flowed inward in smooth, unimpeded streams. No messy accretion disks, no violent outbursts, just a continuous, voracious slurp of cosmic fuel. The answer might lie in the darkest corners of space-time. Next-generation telescopes like the James Webb Space Telescope are now hunting for the faint glow of these black holes' earliest meals, while gravitational wave observatories listen for echoes of their formation. Every new discovery peels back another layer of the mystery, revealing a universe far more inventive and far more relentless than we ever imagined. One thing's certain, the the existence of these ancient giants isn't just a curiosity. They shaped the galaxies around them, carving out the cosmic architecture that made our own existence possible. And hidden within their origins might be clues to something even deeper, the untold story of how chaos forged order in the universe's first fleeting moments. There's a cosmic hide-and-seek game playing out at the edge of the observable universe, and we're only just beginning to grasp the rules. The James Webb Space Telescope, humanity's most powerful eye on the cosmos, has revealed countless galaxies from the cosmic dawn, yet something's missing. Entire populations of early galaxies predicted by theory simply aren't showing up in the data. It's as if the universe's first cities have cloaked themselves in shadows, and the reason might rewrite what we know about how galaxies grow. The leading suspect, cosmic dust. In modern galaxies, dust is commonplace flecks of carbon and silicon forged in stellar furnaces floating among the stars. But in the pristine early universe, dust should have been rare, yet some primordial galaxies appear suspiciously dim, their light smothered by thick veils of this very material. How could dust exist in such abundance before generations of stars had time to create it? One provocative idea suggests supernova from the first stars produced dust at breakneck speeds, seeding their host galaxies far earlier than models predict. Another theory points to massive, unstable stars that shed dust directly as they burned, like cosmic sandstorms in the making, but dust isn't the only culprit. Some galaxies might be hiding in plain sight, their light stretched and reddened by the universe's expansion beyond the wavelengths our telescopes can detect. Imagine trying to spot a firefly behind a fogged-up window while wearing sunglasses. That's the challenge astronomers face when hunting these ancient structures. Even JWST, with its unparalleled infrared vision, hits a wall. The telescope can't see light redder than 28 microns, leaving a blind spot where certain early galaxies might lurk. Then there's the star formation paradox. Some simulations predict a frenzy of star birth in the cosmic dawn, with galaxies churning out suns at rates that should make them blaze across the cosmos. Instead, we're finding fewer bright galaxies than expected. Could these stars have formed differently, perhaps in smaller, dimmer clumps that avoided detection? Or did something suppress star formation entirely, like the crushing gravity of dark matter halos or the harsh radiation from nearby quasars? The answer might lie in a cosmic quirk of timing. The very first galaxies could have been so small and faint that even JWST struggles to spot them, like trying to pick out a single candle on a mountain across an ocean. Others might have lived fast and died young, flaring brilliantly before their gas was stripped away by intergalactic winds, leaving only ghosts in the data. And some could be masquerading as something else entirely, their light distorted by gravitational lensing, or their stars so unlike modern ones that our algorithms overlook them. This isn't just a technical challenge, it's a fundamental gap in our story of cosmic evolution. Every missing galaxy skews our understanding of how matter clustered in the early universe, how quickly structures emerged, and even how the first black holes found their footing. Future telescopes like the planned Habitable Worlds Observatory might extend our vision deeper into the infrared, peeling back these layers of cosmic camouflage. Until then, the invisible galaxies remain both a frustration and a tantalizing clue, proof that the cosmic dawn still holds secrets we've only begun to imagine. Stretching across the vast emptiness between galaxies, an invisible architecture shapes the cosmos, a labyrinth of delicate threads weaving the universe into a single, interconnected web. This is the cosmic web, the scaffolding upon which galaxies are hung, and its structure holds secrets about how the universe organized itself after the Big Bang. Picture it like the root system of a colossal tree, with galaxies clustering at the intersections of these tangled filaments, while rivers of hydrogen gas flow silently along the strands. But here's the catch. This cosmic skeleton is made of such diffuse material that its faint glow has eluded detection for decades, leaving astronomers to piece together its existence through shadows and echoes. Theoretically, the cosmic web should be everywhere. Simulations show that dark matter's gravitational pull first drew matter into wispy tendrils, with gas following like water filling cracks in drying mud. Over billions of years, these filaments grew thicker and more defined, channeling raw material into galaxies like cosmic highways feeding urban centers. Yet actually spotting these threads has been like trying to photograph a spider's web at midnight. Their hydrogen gas emits only subtle ultraviolet light, absorbed almost entirely by Earth's atmosphere. For years, the best evidence came from indirect methods, mapping the positions of millions of galaxies and inferring the web's structure from their distribution, or studying how light from distant quasars filtered through intervening gas like a backlit stained glass window. Then, in 2020, astronomers caught a fleeting glimpse of the web in action. Using the Keck Observatory, they trained their instruments on a filament stretching between two young galaxies 10 billion light-years away. The gas was glowing not from starlight but from the sheer energy of cosmic structure formation itself. As hydrogen funneled along the filament, collisions between particles heated it to millions of degrees, causing it to emit X-rays. This discovery confirmed that the web isn't just a passive framework, it thrums with energy, actively ferrying fuel to growing galaxies. But the deeper mystery lies in what we still can't see. Most of the web's gas should be far colder and far dimmer, emitting only a faint signal called the Lyman alpha forest, a complex pattern of absorption lines in quasar light. Even this whisper is drowned out by foreground noise, like trying to hear a pin drop in a thunderstorm. Some researchers have turned to radio astronomy, hunting for the web's hydrogen via its 21-centimeter emission, but the signals are maddeningly faint. Others are developing algorithms to amplify the cosmic web's signature in existing data, teasing out patterns too subtle for the human eye. The stakes go beyond mere cartography. These filaments may hold clues to one of cosmology's biggest puzzles, the missing baryon problem. Roughly half the ordinary matter in the universe, the protons and neutrons that make up stars, planets, and us, is unaccounted for. The leading theory, it's hiding in the warm, hot intergalactic medium, the diffuse gas of the cosmic web, too thin to emit light but too hot to absorb it. If we could map the web's full structure, we'd not only complete our picture of cosmic evolution, we'd solve a fundamental inventory problem of the universe itself. New tools are tipping the scales. The upcoming square-kilometer array radio telescope promises to scan the sky with unprecedented sensitivity, while advanced spectrographs like those planned for the 30-meter telescope could dissect the web's chemistry in exquisite detail. And then there's the dark horse, gravitational lensing. By measuring how the web's mass warps light from background galaxies, we might finally trace its shadowy outline. What makes this mystery so tantalizing is that we're essentially hunting the universe's circulatory system, the veins that nourished the first galaxies and set the stage for everything that followed. And somewhere in that labyrinth of gas lies the answer to how chaos birthed order, how emptiness gave rise to the glittering cities of stars we see today. The cosmic web isn't just a relic of the past, it's the unseen architect of our present. When the James Webb Space Telescope opened its golden eye to the cosmos, scientists expected to see faint, infant galaxies flickering at the edge of visibility. Instead, they were blindsided by a parade of brilliant, fully formed galaxies blazing from the universe's first chapters far sooner than anyone thought possible. These weren't just dim sparks in the darkness, they were cosmic bonfires shining with the brightness of modern galaxies despite existing when the universe was barely 5% of its current age. This discovery didn't just tweak our models, it threw them into chaos, forcing astronomers to confront a glaring question: how did galaxies grow up so fast? The heart of the mystery lies in timing. According to leading theories, galaxies assemble gradually, pulling in gas over hundreds of millions of years to form stars in a slow, sustained burn. But JWST observations reveal galaxies already massive and mature when the universe was under 400 million years old, a cosmic blink of an eye. Some boast hundreds of billions of stars, rivaling our Milky Way in scale despite having a fraction of the time to grow. It's like finding a skyscraper in the ruins of an ancient city that hadn't yet invented the wheel. One radical explanation suggests the early universe was a far more efficient star factory than we imagined. Instead of the measured, steady pace of modern star formation, gas in the cosmic dawn might have collapsed into stars in violent, runaway bursts, a phenomenon called explosive star formation. Imagine a wildfire versus a campfire. Under the right conditions, entire galaxies could have ignited in frenzied starbursts, converting nearly all their gas into stars in one furious eruption. Supporting this idea, some of these early galaxies show signs of extreme star-forming activity, with stellar birth rates hundreds of times higher than anything seen today. But there's a catch. Even explosive star formation struggles to explain the sheer mass of these galaxies without invoking something else, an unseen boost in the cosmic fuel supply. That's where dark matter's role gets even murkier. Simulations show that if dark matter halos in the early universe were denser or more concentrated than we thought, they could have funneled gas into galaxies at breakneck speeds. Picture a cosmic waterslide. If the gravity wells were steeper, gas would have cascaded into galactic cores almost instantaneously, bypassing the slow drip of modern accretion. Yet this raises another puzzle. Why wouldn't these overfilled galaxies burn out just as quickly, leaving behind dead husks by now? Another tantalizing clue comes from black holes. Some of JWST bright galaxies harbor active supermassive black holes at their centers, their furious feeding emitting enough light to outshine entire star populations. Could these monsters have turbocharged galaxy growth? It's possible. As black holes devour gas, they unleash torrents of energy that can heat surrounding material, paradoxically both quenching and triggering star formation. In the dense, chaotic environments of the early universe, this feedback loop might have worked differently, pushing gas into star-forming pockets rather than blowing it away entirely. The implications are staggering. If bright galaxies were common in the cosmic dawn, our entire timeline of cosmic evolution might need rewriting. Maybe galaxies didn't grow linearly but in fits and starts, with explosive growth phases followed by long quiet periods. Or perhaps the early universe had fundamentally different physics, higher gas densities, stronger turbulence, or even exotic forms of dark matter that no longer exist today. Right now, astronomers are racing to solve this puzzle, combing through JWST data for patterns. Are these galaxies truly typical of their time, or is JWST simply spotting the brightest outliers first? Future observations targeting fainter, more normal galaxies could tip the scales, but one thing's certain: the universe's childhood was far more dramatic than we ever imagined, a time when galaxies didn't just flicker to life but erupted in brilliance, defying every rule we thought we knew. The first stars were pure, born from nothing but hydrogen and helium, the pristine elements forged in the Big Bang's aftermath. Yet somehow, within just a few 100 million years, the cosmos became littered with heavier atoms: carbon, oxygen, iron, even gold. These metals, what astronomers call any element heavier than helium, shouldn't have existed in meaningful quantities until generations of stars lived and died. Their early presence is like finding a stainless steel sword in a Stone Age village, a cosmic anachronism that forces us to rethink how the universe cooked its first heavy elements. The conventional story goes like this: massive stars fuse lighter elements in their cores, building up to iron before exploding as supernova, scattering their enriched remains into space. Over eons, this stardust collects into new stars, planets, and eventually us. But the timeline doesn't add up. ancient quasars, bright beacons powered by supermassive black holes, already show traces of iron when the universe was less than 1 billion years old. That's too soon for multiple stellar generations to have cycled through. So how did these metals appear so quickly, enter the hypernova, a supernova's furious big brother? When the first stars, hundreds of times more massive than our Sun, reached the end of their brief lives, they may have collapsed in explosions so violent they outshone entire galaxies. These hypernovae wouldn't just scatter metals, they'd forge them in unprecedented quantities, flooding surrounding space with heavy elements in a single cosmic blast. Some models suggest hypernova could have produced 10 times more iron than a typical supernova, seeding the early universe with metals far faster than ordinary stellar deaths could achieve. But hypernova might not be the only culprits. Another cosmic alchemist hides in the shadows: neutron star collisions. When these ultra-dense stellar remnants spiral into each other, they unleash gravitational shockwaves and gamma-ray bursts, along with a rain of heavy elements like gold and platinum. Simulations show neutron star mergers could have happened surprisingly early, especially if the first stars left behind an abundance of these compact remnants. A single collision might have ejected enough gold to fill an entire galaxy's worth of solar systems, scattering precious metals across the cosmos before most galaxies had fully formed. Yet the plot thickens. Recent observations of ancient gas clouds reveal another twist. The ratios of these early metals don't quite match predictions. Certain elements like carbon and oxygen appear overabundant compared to iron, hinting at alternative factories, perhaps massive, rapidly spinning stars that shed enriched material in winds before exploding. Others show bizarre zinc signatures, pointing to rare types of supernova we've never witnessed directly. The implications are staggering. If heavy elements spread faster and more chaotically than we thought, they could have jump-started the birth of later stars, altering the chemistry of entire galaxies before they even took shape. Planets and potential life might have had a head start, with rocky worlds forming earlier than expected in cosmic history. Unraveling this mystery requires cosmic forensics. Astronomers now hunt for metal-poor stars in our galaxy's halo, relics from the cosmic dawn whose atmospheres preserve the elemental mix of their birth clouds. Others scour distant quasars for absorption lines that might reveal the fingerprints of hypernova or neutron star debris. With each clue, we're piecing together a new story of cosmic evolution, one where the universe didn't just wake up slowly, but erupted in a fireworks show of creation, scattering the seeds of everything we know in its explosive first act. Deep in the cosmic shadows, a glaring mismatch haunts our understanding of galaxy formation, one that strikes at the very heart of dark matter theory. According to sophisticated simulations, the early universe should be teeming with thousands of tiny satellite galaxies orbiting larger ones like fireflies around a lantern. But when astronomers peer into the depths of space, they find only a pitiful handful. This missing satellites problem isn't just a counting error. It's a cosmic detective story with implications that ripple across physics, challenging everything we thought we knew about how structure emerges in the universe. The roots of this mystery stretch back to the late 1990s, when computer models first simulated how dark matter should clump together after the Big Bang. These simulations painted a vivid picture, a universe frothing with countless small dark matter halos, each a potential cradle for a dwarf galaxy. The math seemed ironclad given how much dark matter outweighs ordinary stuff. There should be at least 10 times more dwarf galaxies around the Milky Way than we've spotted. So where did they all go? One leading theory points to a cosmic massacre. In this scenario, most dwarf galaxies did form, but were brutally stripped of their gas and stars by their larger neighbors. Picture a vast intergalactic battlefield. As these tiny galaxies ventured too close to giants like the Milky Way, gravitational tides ripped them apart, while ultraviolet radiation from newly formed stars boiled away their remaining gas. What's left? Dim, ghostly relics almost entirely made of dark matter, so faint they evade detection unless they happen to drift directly through our line of sight. Recent discoveries of ultra-faint dwarfs, some with just a few hundred stars, support this idea. These cosmic survivors are so diffuse, their starlight barely registers against the blackness of space. But there's a catch. Even adding these ghostly dwarfs to the tally doesn't close the gap. That's led some researchers to question the nature of dark matter itself. Maybe it wasn't cold and sluggish as most models assume, but slightly warm, moving fast enough in the early universe to avoid clumping into so many small halos. Warm dark matter particles would stream through space like a subtle wind, smoothing out the smallest density fluctuations before they could collapse into galaxies. The result, fewer dwarfs overall, matching observations better. Yet this solution introduces new headaches, like explaining how galaxies manage to form at all in such a washed-out cosmic landscape. Then there's the feedback problem. The first stars didn't just shine, they scorched their surroundings with radiation, supernova explosions, and powerful stellar winds. This energetic backlash could have sterilized entire swaths of the early universe, preventing dwarf galaxies from ever getting a foothold. Some simulations show that in regions blasted by early starlight, gas became too hot and agitated to collapse into new stars, leaving potential dwarf galaxies stillborn, dark matter halos with nothing luminous to mark their existence. The stakes couldn't be higher. If our census of dwarf galaxies is wildly off, it doesn't just affect galaxy formation theories, it shakes the foundations of dark matter science. Alternative models, from self-interacting dark matter to exotic quantum fluctuations, are now on the table, each with its own predictions about how many dwarfs should exist and where. New telescopes like the Vera Rubin Observatory aim to settle the debate, scanning the skies for ultra-faint dwarfs that might tip the scales. Hidden in this cosmic discrepancy is a profound lesson. The universe never follows the tidy scripts we write for it. Every time we think we've mapped the rules of structure formation, reality throws us a curveball, and in those surprises lie the clues to deeper truths. Whether the missing dwarfs are hiding in plain sight or never existed at all, their absence speaks volumes about the unseen forces sculpting the cosmos. Some corners of the early universe seem to have cheated the cosmic rules, vast regions where the hydrogen fog lifted suspiciously early, leaving behind bubbles of unexpected clarity in an otherwise murky young cosmos. Picture a dense forest where certain clearings inexplicably remain free of mist while the rest languishes in haze. These anomalies challenge our entire understanding of reionization, the pivotal epoch when starlight first pierced the darkness. Quasars, those brilliant beacons powered by supermassive black holes, offer crucial clues. Their light, traveling billions of years to reach us, carries spectral fingerprints of every gas cloud it passed through. When astronomers analyzed these cosmic barcodes, they found baffling inconsistencies. Some beams showed heavy absorption from neutral hydrogen, as expected in a partially ionized universe. Others slipped through almost unobstructed, as if their path cut through pre-cleared tunnels in space. The implication, reionization didn't happen evenly. It advanced in splotches and bubbles, with some regions becoming transparent while neighboring volumes remained shrouded for millions of years longer. What could create such cosmic pockmarks? One leading suspect is the clustered nature of early galaxies. Where galaxies formed densely, their combined ultraviolet radiation might have carved localized ionization fronts, like campfires melting frost in overlapping circles. Supermassive black holes add another twist. Their intense X-ray emissions could punch through gas clouds more effectively than starlight alone, creating reionization highways along their jets. Recent simulations even suggest cosmic filaments played a role, funneling ionizing radiation along their lengths like fiber optic cables lighting up distant voids. Yet the most perplexing voids defy all these explanations. Some transparent regions stretch hundreds of millions of light-years, far exceeding the influence of any known galaxy cluster. Could dark matter's uneven distribution have left these areas gas-poor from the start? Or did exotic phenomena, like evaporating primordial black holes or decaying dark matter particles, contribute extra ionizing energy? The answer might lie in the universe's very first microsecond. Quantum fluctuations during cosmic inflation could have seeded slightly denser or sparser patches, setting the stage for this patchwork transparency billions of years later. Every new observation deepens the intrigue. The latest James Webb data reveals galaxies in these clear zones have distinct properties: higher metal content, older stellar populations, hinting they formed in a head start environment. Meanwhile, radio telescopes hunt for the telltale static of hydrogen in the voids, probing whether these regions were truly empty or merely ionized earlier than their surroundings. This isn't just academic curiosity. The pattern of reionization shaped where and how galaxies could grow, ultimately determining the universe's large-scale structure. Those early transparent bubbles became the cosmic nurseries where modern galaxy clusters first took root. By decoding their origins, we're not just solving a regional anomaly, we're reading the hidden blueprint of how light triumphed over darkness. In the constellation Cetus, nearly 13 billion light-years away, a galaxy shines with impossible brilliance, a cosmic beacon from the universe's toddler years that defies all expectations. This is Cosmos Redshift 7, or CR7, discovered in 2015 and still baffling astronomers with its sheer luminosity. What makes this ancient galaxy so extraordinary isn't just its distance, it's the eerie purity of its light, a spectral fingerprint suggesting it might harbor the holy grail of cosmic archaeology, the universe's very first stars. CR7's light profile is unlike anything seen in later galaxies. Its spectrum shows a startling absence of heavy elements, dominated instead by helium's unmistakable glow, a hallmark of population 3 stars, those mythical giants forged from nothing but primordial hydrogen and helium. These stellar pioneers, hundreds of times more massive than our Sun, would have burned blisteringly hot and blue, their ultraviolet radiation ionizing the surrounding gas with unprecedented efficiency. If CR7 truly hosts these stars, it would be like stumbling upon a living relic from the cosmic dawn, a snapshot of star formation in its purest, most violent form. But there's a twist. Another explanation lurks in the shadows, one just as tantalizing. CR7's brilliance could also signal a monster lurking at its heart, a supermassive black hole devouring matter at a ferocious rate. Active black holes, especially in the early universe, often outshine their host galaxies, their accretion disks glowing white-hot as gas spirals inward. This scenario would rewrite CR7's story entirely. Instead of a nursery for first-generation stars, it might be a cosmic furnace powered by gravity's darkest trick. The debate hinges on subtle clues. Population 3 stars should emit specific wavelengths of helium-2 radiation, while black holes produce a broader spectrum of high-energy X-rays and ultraviolet light. Early observations tentatively favor the star hypothesis, but the data remains frustratingly ambiguous. Complicating matters, CR7 shows signs of being chemically polluted in some regions, pockets where heavier elements like carbon and oxygen have already appeared. If population 3 stars existed here, they must have died in supernova explosions, seeding their surroundings with metals while somehow leaving other areas pristine. The stakes couldn't be higher. If CR7's light comes from population 3 stars, it would confirm decades of theory about how the first stellar generations shaped the cosmos. These stars weren't just luminous, they were cosmic alchemists, transforming the universe's simple beginnings into the complex chemistry that made planets and life possible. But if a black hole is masquerading as starlight, it would force us to reconsider how quickly these gravitational monsters could grow, and what role they played in lighting up the early universe. New observations might finally settle the argument. The James Webb Space Telescope's infrared eyes are ideally suited to dissect CR7's light with unprecedented precision, searching for the telltale signatures of helium or the smeared emission lines characteristic of a black hole's accretion disk. Meanwhile, radio telescopes scour the galaxy for the faint whisper of hydrogen gas stirred by stellar winds or black hole jets. CR7 is more than a cosmic oddity. It's a Rosetta Stone for decoding the universe's turbulent adolescence. Whether its brilliance stems from the first stars or an early black hole, this enigmatic galaxy holds secrets about how darkness gave way to light and how chaos birthed the ordered cosmos we call home. Before the first stars flickered to life, the universe endured an epoch of profound quiet, an era astronomers call the Dark Ages. This was not merely an absence of light, but a period of cosmic incubation where hydrogen gas stretched across the void in vast, undisturbed clouds. These primordial reservoirs hold secrets far beyond their simplicity, acting as frozen relics of a time before chemistry, before structure, before the universe had taken its first breath. Neutral hydrogen atoms untouched by starlight was the universe's first and only ingredient in this era. Without stars to ionize it, this gas hung in perfect darkness, its behavior governed solely by the whisper of gravity and the faint echoes of the Big Bang's afterglow. But hidden within these seemingly inert clouds were the subtle stirrings of something extraordinary, the earliest hints of molecular formation. When temperatures dipped low enough in certain pockets, hydrogen atoms paired up to form hydrogen molecules, the fragile building blocks of pre-stellar chemistry. These delicate pairings, though fleeting, might have set the stage for the universe's first collapse into stars. The key to unraveling this era lies in the 21-centimeter line, a faint radio signal emitted by neutral hydrogen as its electron spins flip direction. By mapping this signal across the cosmos, astronomers can essentially peer back to the Dark Ages, tracing how hydrogen clumped and moved before stars reshaped everything. Some theorists suggest these maps might reveal unexpected patterns, wrinkles in the fabric of space where dark matter's pull was particularly strong, or ghostly sound waves left over from the Big Bang itself. Others speculate that traces of early molecules like hydrogen deuteride or lithium hydride could still linger in the data, acting as chemical fossils from a time before fusion lit up the cosmos. There's even a wilder possibility that the Dark Ages weren't entirely dark. Exotic particles or evaporating black holes might have emitted faint glows barely perceptible against the void. Or perhaps quantum fluctuations sparked brief, ephemeral structures, cosmic mayflies that flickered into existence and vanished before they could leave more than a ripple. Unlocking these mysteries would do more than satisfy scientific curiosity. It would reveal the universe's raw potential, the quiet moments before creativity exploded into light. Every galaxy, every star, every atom in our bodies owes its existence to how hydrogen navigated this silent era, an epoch we're only now learning to hear. Cosmic structures shouldn't exist, at least, not as soon as they did. Simulations of the early universe paint a careful picture. Matter slowly clumping together under gravity's pull, taking billions of years to build the vast galaxy clusters we see today. But observations tell a radically different story. Ancient megastructures, colossal groupings of galaxies bound together like cosmic cities, appear fully formed when the universe was less than a quarter of its current age. It's as if the cosmos skipped half the steps in its own instruction manual, leaving astronomers scrambling to explain how gravity could have worked overtime in the universe's youth. Take the El Gordo cluster, a behemoth lurking 9 billion light-years away. This titanic assembly of galaxies weighs in at over 3 quadrillion times the mass of our Sun, making it one of the largest structures known at such an early epoch. According to standard models, a cluster this massive should have taken nearly the entire age of the universe to assemble. Yet here it is, strutting across the cosmos when the universe was barely 6 billion years old. Even more puzzling, its galaxies move at terrifying speeds, suggesting they're bound by far more gravity than visible matter can account for. Either dark matter behaved differently in the past, or our understanding of cosmic growth is missing a fundamental piece. Theories abound. One provocative idea suggests that dark matter wasn't entirely cold and sluggish in the early universe, but slightly warm, moving fast enough to smooth out small clumps while still allowing massive structures like El Gordo to form at record speed. Another explanation points to cosmic inflation's quirks. Perhaps quantum fluctuations in the universe's first moments planted over dense seeds that grew into ready-made gravitational wells, funneling matter into clusters far quicker than gradual accretion could achieve. Then there's the wild card primordial black holes. If these ancient gravitational pits existed in vast numbers, their extra pull might have jump-started structure formation, acting as anchors for galaxies to swarm around. Yet none of these fully resolve the tension. Computer simulations incorporating known physics consistently produce cosmic webs that evolve too slowly to match the metropolis-like clusters we observe. Some researchers argue the discrepancy might lie in feedback mechanisms we've underestimated, like supermassive black holes spewing jets of energy that heated surrounding gas, preventing small galaxies from forming and forcing matter to collect only in the deepest gravitational valleys. Others wonder if gravity itself operated differently under extreme early universe conditions, its strength subtly enhanced by hidden dimensions or unknown particle interactions. The James Webb Space Telescope has added fresh fuel to the fire. Its deep field images reveal protoclusters, infant versions of galaxy clusters, already taking shape when the universe was under 2 billion years old. These embryonic giants shouldn't exist according to textbook timelines, yet they glow defiantly in the data, their galaxies packed unusually close together. Even more perplexing, some show evidence of having already experienced multiple generations of star formation, implying their constituent galaxies matured at breakneck speed. Solving this mystery could rewrite cosmology's rulebook. If structures formed faster than gravity alone allows, it might hint at exotic physics, extra forces, dynamic dark energy, or even flaws in Einstein's relativity at cosmic scales. Or perhaps the answer is simpler. Maybe the universe's starting conditions were far more dramatic than we've assumed, with matter distributed in ways that turbocharged clustering from the very beginning. Every new observation peels back another layer, revealing a cosmos that built itself with startling efficiency, defying our neat theoretical boxes. One thing's certain, the early universe didn't dawdle. It built with purpose, as if racing toward some unseen finish line, and we're only just beginning to glimpse the urgency behind its ancient construction spree. Among the faint whispers of the early universe, astronomers have stumbled upon an enigma that shouldn't exist, a mysterious hum of radio waves permeating the cosmos, drowning out the subtle signals we're desperate to hear. This is the anomalous radio background, a puzzling static that blankets the sky at wavelengths where we expect near silence. Its presence isn't just an inconvenience, it's a potential game-changer, warping our ability to detect the 21-centimeter signal from the cosmic dawn and hinting at phenomena we've yet to imagine. The 21-centimeter signal is astronomy's holy grail for probing the universe's infancy, a whisper from neutral hydrogen that carries secrets about the first stars and galaxies. But this ghostly fingerprint is delicate, easily masked by even faint interference. When researchers first mapped the radio sky, they expected to account for all the noise, the murmur of distant galaxies, the crackle of supernova remnants, even the faint glow of our own Milky Way. What they found instead was an excess of radio waves, a background hiss up to twice as loud as all known sources combined. It's like tuning a radio between stations and hearing static far louder than any broadcast should allow. Where is this noise coming from? One camp points to undiscovered astrophysical sources, countless faint galaxies too dim to spot individually, their combined radio emissions blending into a diffuse fog. Simulations suggest these could be dwarf galaxies, their star formation less efficient but more numerous than we've accounted for. Others propose a zoo of exotic objects, rogue planets with powerful magnetospheres, never before seen pulsar varieties, or even dark matter annihilating into radio waves in the voids between galaxies. But the wildest theories venture beyond conventional physics. Some speculate this noise could be the echo of primordial black holes evaporating via Hawking radiation, their death throes releasing bursts of low-frequency waves. Others wonder if it's evidence of action's hypothetical dark matter particles converting into photons in the presence of cosmic magnetic fields. There's even a fringe idea that the anomalous background might be a relic of the universe's birth, a signature of quantum foam fluctuations frozen into the fabric of space-time itself. The stakes are immense. If the noise stems from undiscovered astrophysics, it could mean our census of cosmic objects is wildly incomplete. If it's tied to new physics, we might be glimpsing a shadow universe of particles or forces operating just beyond our current models. Future radio telescopes like the Square Kilometre Array aim to peel back this interference, mapping the 21-centimeter signal in unprecedented detail. Until then, the anomalous radio background remains both an obstacle and a clue, a reminder that the universe still hums with secrets we've only begun to hear. Stretching across the black voids between galaxies, a faint, ghostly luminescence defies the darkness, an eerie glow known as intracluster light. This isn't starlight from any single galaxy, but the cosmic aftermath of violent collisions where entire galaxies ripped each other apart, scattering their stars into the abyss like glitter tossed into the wind. What makes this glow so extraordinary isn't just its beauty, it's the secrets it holds about the cosmic dawn, a time when the universe's first galactic structures were forged in chaos. Most of this light comes from orphaned stars, lonely giants flung far beyond their home galaxies during cataclysmic mergers. In modern galaxy clusters, we see these stars as a diffuse haze, so faint that it takes hours of telescope exposure to reveal their collective shimmer. But in the early universe, the glow would have been far dimmer, drowned out by the brilliance of newborn galaxies. Yet somehow, traces of it linger, preserving a record of the universe's most violent formative moments. The key lies in the patterns. Intracluster light isn't random, it forms delicate streams and shells, the gravitational fingerprints of ancient collisions frozen in time. One leading theory suggests these stars weren't just scattered haphazardly. During the cosmic dawn, as proto-galaxies clashed in the densest regions of the young cosmos, their tidal forces stripped away outer layers of stars, leaving behind trails like cosmic breadcrumbs. Simulations show these encounters would have been frequent and brutal, with smaller galaxies shredded like tissue paper as they spiraled into larger neighbors. Over time, the stripped stars settled into a smooth glow, filling the spaces between galaxies like smoke filling a room. But here's the twist: some intracluster light appears too old, too spread out to fit this narrative. Certain clusters, like the famous Coma cluster, host stars that seem to have been wandering the void for nearly as long as the universe has existed. Could these be relics of the very first galactic mergers, events so ancient they predate most of the galaxies we see today? Or did some stars form in the darkness between galaxies, condensing directly from primordial gas without ever belonging to a galactic home? The answer might rewrite the story of how galaxies grew. If intracluster light was already prevalent in the cosmic dawn, it would mean mergers shaped the universe far earlier and more aggressively than we thought. Instead of galaxies evolving in isolation, they might have been born into a cosmic battlefield, their fates intertwined from the beginning. Recent observations from the Hubble and James Webb telescopes have spotted hints of this early intracluster light, faint, bluish tendrils stretching between infant galaxies, suggesting the glow isn't just a modern phenomenon, but a fundamental thread in the tapestry of cosmic evolution. Unlocking this mystery could reveal more than just the history of galactic collisions. The distribution of intracluster light traces the gravitational scaffolding of dark matter, mapping where invisible mass clusters even when galaxies don't. It might also hold clues about lost galaxies, entire systems torn apart so completely that only their scattered stars remain, their existence erased save for this ghostly afterglow. As telescopes grow more sensitive, astronomers are closing in on the cosmic dawn's intracluster light, searching for its spectral signatures in the deepest voids. Each flicker of this ancient glow is a message from a time when the universe was still assembling itself, a reminder that even in the darkest spaces, the echoes of creation still shine. Quasars should have been everywhere in the cosmic dawn, blazing beacons signaling the awakening of the universe's first supermassive black holes. Yet when astronomers scour the earliest epochs, they find a glaring absence. Quasars are vanishingly rare when the universe was younger than 700 million years old. This isn't just a minor discrepancy, it's a full-blown cosmic whodunit with implications that stretch from black hole formation to the very nature of the early universe itself. Picture the scene: an infant cosmos, its first galaxies just sputtering to life, their cores ripe for the birth of monstrous black holes. According to our best models, these gravitational giants should have immediately begun feasting on surrounding gas, lighting up as quasars, some of the brightest objects in existence. But the numbers don't add up. While simulations predict hundreds of quasars glowing in the cosmic dawn, observations reveal only a handful. It's like expecting a bustling metropolis and finding a ghost town instead. One clue lies in the black hole seeding problem. For quasars to ignite, supermassive black holes needed a head start, either born large from collapsing gas clouds or growing at impossible speeds. If early black holes started small, as the remnants of the first stars, they'd have needed billions of years to reach quasar-scale masses, but the universe was too young for that timeline. This suggests most early black holes lacked the ideal conditions to balloon quickly. Perhaps gas in their host galaxies was too turbulent, or star formations siphoned away their fuel before they could binge-eat their way to supermassive status. Another twist comes from accretion physics. Modern black holes often flicker between feast and famine, their growth throttled by the intense radiation they emit while consuming matter. But in the cosmic dawn, the rules might have been different. Without heavy elements to cool the gas, feeding could have been erratic, sporadic bursts of growth followed by long droughts. Some black holes may have choked on their own hunger, blowing away their gas supply with violent outbursts before reaching quasar brightness. Yet there's a wild card: obscuration. What if early quasars aren't missing at all, but hiding behind thick veils of dust and gas? In the chaotic environments of young galaxies, furious star formation could have shrouded black holes in dense cocoons, muffling their light. The James Webb Space Telescope has already spotted a few of these buried quasars in slightly later epochs, their brilliance dimmed to a smolder by intervening material. If this were common in the cosmic dawn, it would mean we're not seeing a quasar shortage, just a universe playing peekaboo with its brightest monsters. The stakes are high. Quasars didn't just light up the early universe, they shaped it. Their radiation ionized hydrogen, their jets stirred up interstellar gas, and their gravity anchored the growth of galaxies. If they were truly scarce in the cosmic dawn, it would mean the universe's transformation from darkness to light was a slower, more uneven process than we've assumed. Or perhaps we've underestimated nature's creativity. Maybe the first black holes grew not through steady feeding, but in explosive, runaway collapses that left few survivors. Right now, astronomers are racing to solve this riddle. New instruments like the Vera Rubin Observatory will scan the skies for overlooked quasars, while advanced simulations test whether early black holes faced unique growth barriers. Every discovery or non-discovery adds another piece to the puzzle, because in the end, the quasar shortage isn't just about missing objects. It's a cosmic clue about how the universe learned to turn chaos into structure and how darkness first gave way to light. To peer back into the cosmic dawn, astronomers turn to an unlikely messenger, not starlight but shadow. When the brilliant glare of a distant quasar races across the universe toward Earth, it doesn't travel undisturbed. Along its billion-year journey, that light passes through countless clouds of hydrogen gas, each one stealing a tiny bite of brightness at a very specific wavelength, the Lyman alpha line. The result, a quasar's spectrum becomes a cosmic barcode, striped with dark absorption lines that betray every hydrogen cloud it encountered. This intricate pattern, known as the Lyman alpha forest, isn't just noise, it's a time machine, preserving snapshots of the universe's youth in threads of missing light. What makes these absorption lines so revealing is their spacing and depth. Tightly packed lines suggest dense thickets of hydrogen, while gaps hint at bubbles where the gas has been ionized, cleared out by the ultraviolet fury of early stars or black holes. By mapping these patterns across thousands of quasars, astronomers have reconstructed a 3D atlas of the cosmic dawn's gaseous landscape, revealing a universe in transition. Some regions appear as Swiss cheese, riddled with ionization bubbles where galaxies blaze to life. Others remain stubbornly opaque, vast hydrogen jungles untouched by starlight. But the forest holds deeper secrets. The width of individual lines encodes the temperature and motion of the absorbing gas. Narrow lines imply cold, placid clouds, pristine remnants of the dark ages. Broad lines betray violence, gas heated by supernova or stirred by galactic winds. Occasionally, lines cluster at specific redshifts, tracing the ghostly outlines of cosmic filaments, those dark matter tendrils that channeled gas into the first galaxies. Perhaps most tantalizing are the Lyman alpha troughs, regions where absorption lines vanish entirely. These aren't blanks in the data, but evidence of fully ionized highways carved by extreme radiation sources. Some may point to the locations of the first quasars, their brilliance so intense it sterilized entire intergalactic arteries. Others could mark where dark matter decayed into radiation, adding an unexpected push to reionization. Now, new telescopes like the James Webb Space Telescope and upcoming 30-meter class observatories are decoding finer details in this forest, measuring trace elements like deuterium and helium that reveal the gas cloud's origins. Each line of absorption is a sentence in the universe's diary, written in the language of missing light, and as we learn to read it more fluently, we're uncovering not just how the cosmic dawn unfolded, but where the raw materials for life itself first began their journey. In the searing chaos of the cosmic dawn, where ultraviolet radiation from newborn stars and quasars scorched everything in its path, astronomers have stumbled upon something astonishing: pockets of impossibly cool gas, chilling against all odds in the cosmic furnace. These cold reservoirs, detected in galaxies barely a billion years old, shouldn't exist, not here, not when the universe was still a battleground of blistering energy. Yet they linger like ice cubes in a bonfire, defying every expectation of how gas behaves in the early universe. The discovery came from an unlikely source, delicate fingerprints in the light of distant quasars. As their beams pierced ancient galaxies, certain wavelengths were absorbed not by the expected superheated plasma, but by molecules: carbon monoxide, water vapor, even simple organic compounds, all traces of gas cool enough to form intricate structures. In modern galaxies, this wouldn't raise eyebrows, but in the cosmic dawn, it's like finding an air-conditioned room in the middle of a volcano. How did these cold pockets survive? One clue lies in their hiding places. Simulations suggest the gas might have shielded itself in dense cocoons, layers upon layers of molecular hydrogen acting like cosmic insulation against the ultraviolet onslaught. Picture a snowball wrapped in layers of foil tossed into a fire. The outside might scorch, but the core stays frozen. Some galaxies may have funneled their gas into deep gravitational wells where sheer pressure kept it cool despite the surrounding inferno. Others could have relied on an unexpected ally, dust. Yes, dust, those microscopic flecks of carbon and silicon that shouldn't have been abundant so early. Yet there they are, detected in some of these ancient systems. Dust grains are phenomenal radiators, shedding heat efficiently into space. If enough of them peppered the gas clouds, they could have acted like a cosmic refrigeration system, bleeding away thermal energy faster than starlight could replenish it. The implications are staggering. If dust spread this quickly, the first supernova must have been far more productive than we imagined, seeding their galaxies with heavy elements almost immediately after the first stars died. But the plot thickens. Some cold gas reservoirs show signs of turbulence, violent, churning motions that suggest they weren't just passively cooling, but actively fighting to stay cold. Galactic winds driven by supernova or black hole jets might have compressed the gas into tight knots where it radiated heat away rapidly. Or perhaps magnetic fields threading through the clouds like invisible spiderwebs stabilized them against disruptive radiation, creating microclimates of cold in an otherwise scorching universe. The survival of this gas isn't just an academic curiosity. Cold gas is the raw material of star formation. Where it persists, stars can birth in abundance, shaping galaxies for eons to come. These reservoirs might explain why some early galaxies formed stars at breakneck speeds while others stalled. A cosmic divide between haves and have-nots, dictated by who could keep their gas cool under pressure. Now, telescopes like ALMA and the James Webb Space Telescope are hunting for more of these icy anomalies, probing their chemistry and structure. Each discovery peels back another layer of the mystery, revealing a cosmic dawn far more nuanced than we ever imagined. A time when the universe wasn't just a uniform inferno, but a patchwork of extremes where pockets of tranquility somehow endured against the odds. And hidden in these cold, ancient clouds might lie the secrets of how galaxies learned to thrive in the furnace of creation. Deep in the turbulent hearts of the cosmic dawn's first galaxies, a paradox raged, violent storms of gas fleeing outward even as new stars fought to coalesce. These protogalactic winds, powerful enough to fling entire solar systems worth of material into the void, shouldn't have existed in such fragile infant galaxies. Yet the evidence is etched across the cosmos, fingerprints of frantic outflows detected in ancient quasars, ghostly remnants of winds that once shaped the universe's earliest structures. Picture a fledgling galaxy, its core alive with the birth cries of population 3 stars. As these stellar titans ignited, their radiation blasted surrounding gas with the force of 1,000,000 solar flares, while supernova explosions added fuel to the fire. Normally, gravity would keep this chaos contained, but in the cosmic dawn, something extraordinary happened. The combined fury of starlight and explosions overcame gravity's grip, propelling gas outward at speeds exceeding 1,000,000 miles per hour. These weren't gentle breezes but cosmic hurricanes, carrying enough energy to strip entire galaxies of their star-forming fuel. The irony: these destructive winds might have been essential for galactic survival. Simulations reveal a delicate feedback loop. As winds cleared central regions, they prevented new stars from consuming all available gas in one frenzied burst. Instead, the ejected material cooled in intergalactic space, eventually raining back down in orderly cycles, nature's way of pacing stellar birth. Some gas was flung so far it became part of the cosmic web itself, seeding future generations of galaxies with recycled ingredients. Even more astonishing, these winds carried the first heavy metals forged in stellar cores, scattering them far beyond their birthplaces. Metal dispersal holds another layer of intrigue. Astronomers studying quasars 12 billion light-years away found ion absorption lines spread uniformly across intergalactic space, a telltale sign of winds distributing elements far earlier than models predicted. This wasn't slow leakage but explosive injection, like a chef violently shaking salt across a vast cosmic kitchen. The implications rewrite stellar chemistry's timeline. If metals spread this rapidly, second-generation stars might have formed with enriched material much sooner than we thought, accelerating the universe's journey toward complexity. Yet mysteries linger. Some ancient galaxies show evidence of winds powerful enough to escape their host entirely, while others appear oddly calm. What determined which galaxies kept their gas and which blew it all away? The answer might lie in dark matter halos, their mass and shape potentially acting as cosmic windbreaks or accelerators, or perhaps magnetic fields twisting through young galaxies like invisible spiderwebs, channeled outflows along specific paths, leaving some regions untouched. New observations add twists to the tale. The James Webb Space Telescope recently spotted galaxies from the cosmic dawn with bizarre bipolar outflows, jets of material ejected in opposite directions like cosmic geysers. These structures suggest central black holes might have teamed up with stars to sculpt winds with surgical precision, carving cavities where future stars could form in peace. Meanwhile, radio telescopes detect echoes of hydrogen pushed into intergalactic space, its faint 21-centimeter whisper tracing wind patterns frozen in time. The true genius of these outflows lies in their duality. They were both destroyers and architects, quenching star formation in one region while nurturing it in another, dispersing metals yet allowing them to cool and coalesce elsewhere. Without protogalactic winds, the universe might have burned through its gas too quickly, leaving nothing but dead galaxies in its wake. Instead, these violent breaths gave cosmic evolution its rhythm, turning chaos into order one stellar gust at a time. Galaxies separated by billions of light-years should be as diverse as snowflakes, each sculpted by local conditions into unique shapes and sizes. Yet when astronomers peer back to the cosmic dawn, they uncover something startling: distant galaxies growing in eerie sync, as if orchestrated by some unseen cosmic conductor. This synchronization isn't just puzzling, it's a direct challenge to our understanding of how the universe builds structure. How could galaxies so far apart with no possible contact follow such similar evolutionary paths? One clue lies in their shared environment. Early galaxies didn't form in isolation. They were born into a universe still vibrating from the Big Bang's aftermath. Cosmic filaments, vast threads of dark matter and gas, acted like invisible highways, channeling raw materials into galaxies at similar rates across the cosmos. Picture a forest growing from a single water table. Though trees stand apart, their roots tap into the same nourishing source, driving synchronized growth. Simulations show that in regions where these filaments intersected most densely, galaxies feasted on gas simultaneously, igniting stars in unison despite their separation. But there's a twist. Dark matter might not have been the silent scaffold we've assumed. If it interacted weakly with itself or radiation, it could have smoothed out density variations, creating pockets where galaxies experienced nearly identical conditions. Imagine two chefs working in separate kitchens, but given identical ingredients and recipes, their dishes would turn out remarkably alike. Some theories even suggest dark matter carried imprints from the universe's first moments, quantum fluctuations frozen into its distribution, planting the seeds for later synchronization. The plot thickens when we consider feedback loops. The first stars and black holes didn't just shine, they sculpted their surroundings with radiation and shock waves. In galaxies of similar mass, these processes could have self-regulated growth with matching precision. Too much star formation, intense radiation blows away gas, throttling further growth. Too little, gravity pulls in fresh fuel, reigniting the cycle. Like pendulums swinging in harmony, galaxies might have settled into parallel rhythms, their development dictated by universal physics rather than local chaos. Yet contradictions remain. Some galaxy clusters show near-perfect synchronization, while others display wild disparities. Could this variation hint at deeper cosmic divisions, regions where dark matter behaved differently, or where the primordial soup was stirred unevenly? Radio telescopes scanning for hydrogen's faint whispers and next-generation observatories mapping dark matter's shadowy web aim to crack this code. The answer might redefine our place in the cosmos. If synchronization stems from dark matter's hidden rules, we're glimpsing the invisible hand that shaped all structure. If it's a relic of the Big Bang's first vibrations, we're hearing echoes of creation itself. Either way, these mirrored galaxies are more than curiosities. They're cosmic breadcrumbs leading us toward the laws that bound the universe together in its infancy. Black holes shouldn't be able to grow this fast. In the cosmic dawn, supermassive black holes weighing billions of suns appear fully formed when the universe was barely old enough to blink, far too soon to have grown from the depths of ordinary stars. This glaring cosmic speed limit has split astronomers into opposing camps, each with a radical theory about how gravity's most monstrous creations cheated time. On one side, the slow and steady camp, convinced these black holes grew from stellar corpses through relentless feeding. On the other, the direct collapse revolutionaries, arguing some black holes were simply born gigantic, skipping stellar adolescence entirely. The stellar remnant theory has elegance on its side. When massive stars die, their cores collapse into black holes, typically just a few times the sun's mass. Given enough gas and enough time, these seeds could theoretically gorge themselves into supermassive status, but the math strains credulity. Even feasting at the maximum possible rate, a process called Eddington-limited accretion, a stellar mass black hole would need nearly 1 billion years to reach quasar-scale masses. Yet we're finding billion solar mass black holes when the universe was barely half that age. To make the timeline work, some propose brief periods of super-Eddington feeding, where black holes devoured gas so rapidly they blew past theoretical limits. Imagine trying to drink from a fire hose. Most would spill more than they swallow, but perhaps early black holes had cosmic tricks to guzzle efficiently. Then there's the fuel problem. Modern black holes often flicker between feast and famine as radiation pressure blows away their gas supply. But in metal-poor early galaxies, gas might have flowed inward in smooth, cold streams, no messy accretion disks, no violent outburst. Recent simulations show these pristine conditions could have sustained near-constant feeding, like a perfectly tuned intravenous drip of cosmic fuel. Yet even this best-case scenario barely squeezes into the observed timeline, leaving astronomers uneasy. The direct collapse alternative is bolder. Picture a vast cloud of primordial hydrogen, unpolluted by heavy elements, collapsing under its own weight. Without metals to cool and fragment the gas, the entire cloud, hundreds of thousands of solar masses, could implode directly into a black hole, no star required. These behemoth seeds would have had a head start, needing far less time to grow into the quasars we observe. The catch: this process requires near-mythic conditions, gas clouds untouched by starlight or turbulence, cooling just enough to collapse but not enough to splinter into stars first. Some theorists argue such pristine pockets must have been vanishingly rare, yet the abundance of early quasars suggests otherwise. A third possibility bridges the divide. Maybe both paths happened. Stellar remnants could have dominated in some regions, while direct collapse monsters emerged in others. Evidence might lie in the black hole spins. Slowly grown black holes tend to rotate faster, their angular momentum building over countless meals. Direct collapse black holes born from monolithic implosions should spin more sluggishly. Current measurements are too fuzzy to confirm, but next-generation gravitational wave detectors could settle the debate by analyzing mergers from the cosmic dawn. The answer isn't just academic, it shapes how we understand galaxy formation itself. black holes aren't passive residents, their growth and feedback sculpt their hosts. If they grew via direct collapse, their violent births might have ignited star formation across entire proto-galaxies. If they clawed their way up from stellar seeds, their slower rise could explain why some early galaxies matured faster than others. Every new observation peels back another layer, revealing a universe that found multiple paths to forge its darkest wonders. The missing link in black hole seeds isn't just a puzzle about gravity, it's a window into the ingenuity of cosmic evolution itself. Somewhere in the static of the cosmos, buried beneath the chatter of stars and galaxies, lies the faintest whisper from the dawn of time itself. Ripples in the fabric of space-time known as primordial gravitational waves. These elusive tremors, echoing from the first moments after the Big Bang, carry secrets about the universe's earliest convulsions. Yet despite decades of searching, they remain just beyond our grasp, drowned out by the noise of modern detectors and the sheer scale of cosmic time. The hunt for these waves is like trying to hear a pin drop in a hurricane. Current observatories like LIGO and Virgo are exquisitely tuned to catch gravitational waves from black hole mergers and neutron star collisions, events that shake spacetime with staggering force. But primordial waves are different. Born from quantum fluctuations amplified during cosmic inflation, these ripples would have stretched across the universe as it expanded, their wavelengths now spanning light years. Detecting them would be like trying to measure the rise and fall of an ocean tide with a teaspoon. The challenge isn't just technological, it's fundamental. Primordial waves would imprint a distinct curl pattern, or B-mode polarization, on the cosmic microwave background, the afterglow of the Big Bang. Experiments like BICEP and Planck have scoured the sky for this signature, but so far, interstellar dust and other foreground interference have muddied the signal. It's as if we're trying to read a message written in fog, with every gust of wind scattering the letters before we can piece them together. Even if we could isolate the signal, today's detectors lack the sensitivity to measure waves from the cosmic dawn. The frequencies we're after are absurdly low oscillations that might take years or even centuries to complete a single cycle. Ground-based interferometers built to catch high-frequency ripples are deaf to these cosmic bass notes. To hear them, we'd need an observatory spanning millions of kilometers in space, like the proposed LISA mission, or a lunar-based detector using the moon itself as a resonant drumhead. The stakes couldn't be higher. Primordial waves would confirm whether cosmic inflation truly happened, revealing how the universe ballooned from subatomic to cosmic scales in less than a trillionth of a second. They might even hint at physics beyond Einstein quantum gravity, extra dimensions, or a multiverse of bubble universes. Every null result isn't a failure but a clue, narrowing the range of possible theories. For now, the whispers remain just out of earshot, taunting us with their silence, but the hunt continues, pushing detectors to new extremes and inspiring ingenious workarounds. Some propose tracking pulsars as natural gravitational wave antennas, while others dream of atomic interferometers in deep space. One day, when the right tool finally listens in the right way, those whispers might roar, and the cosmic dawn will speak at last. Galaxies spinning in perfect alignment across vast cosmic distances shouldn't happen by chance. Yet when astronomers mapped the rotation axes of thousands of early galaxies, they found something startling. Many were spinning in sync, their orientations eerily coordinated like dancers in a cosmic ballet. This bizarre phenomenon, stretching across billions of light years, defies the randomness we'd expect from a universe built on chaos. What invisible hand could have steered these galaxies into such harmonious motion? One explanation tugs at the fabric of spacetime itself. During the universe's infancy, colossal magnetic fields threading through the cosmos like invisible strings might have imprinted a preferred direction on swirling gas clouds. As these clouds collapsed into galaxies, their spins could have locked into alignment with these primordial fields, much like iron filings arranging themselves along a magnet's lines of force. Supporting this idea, radio telescopes have detected faint magnetic signatures in some of the universe's oldest gas clouds, their polarization patterns hinting at large-scale order. But here's the puzzle: magnetic fields weaken over time, and their influence should have faded long before galaxies formed, unless, of course, something kept them alive, perhaps turbulent motions in the cosmic web, or even dark matter acting as an unseen catalyst. Then there's dark matter's hidden flow. Simulations suggest the early universe wasn't a static arena but a dynamic river of dark matter, streaming along filaments in coherent currents. If galaxies formed within these flows, their spins might have been dragged into alignment like leaves caught in a whirlpool. The darkest regions of the cosmos, voids where matter is scarcest, could hold clues. Here, galaxies show the strongest alignment trends, as if their spins were frozen in place by the pull of dark matter's ancient tides. Yet this raises another question: why don't modern galaxies display the same synchronicity? Perhaps as the universe expanded, these flows diluted, their organizing influence fading into the background hum of cosmic evolution. The plot thickens when we consider alternative theories. Could gravitational waves from the Big Bang itself have twisted spacetime on a cosmic scale, leaving behind a faint rotational bias? Or did quantum fluctuations during inflation, the universe's explosive first moments, set off a chain reaction that ultimately dictated how galaxies would spin? Some models even suggest that the alignment isn't real at all, but an illusion caused by the way galaxies cluster along filaments, their orientations appearing coordinated from our vantage point. The implications ripple far beyond galactic spin. If alignments stem from primordial magnetism, they'd imply the early universe was far more structured than we thought, a place where forces beyond gravity sculpted the cosmos in ways we're only beginning to grasp. If dark matter flows are the culprit, we might need to rethink its nature, imagining it not as a passive scaffold but as an active sculptor of galactic destiny. New telescopes like the Square Kilometre Array aim to settle the debate, mapping the polarization of ancient hydrogen to trace magnetic fields frozen in time. Meanwhile, advanced simulations are recreating the cosmic dawn with unprecedented detail, testing whether virtual galaxies spin in sync under different starting conditions. Every observation tightens the net around this cosmic conundrum, pulling us closer to an answer that could rewrite our understanding of structure formation. What makes this mystery so captivating isn't just the alignment itself, but what it reveals about the universe's hidden architecture. Galaxies aren't isolated islands, they're threads in a grand tapestry, woven together by forces we've yet to fully comprehend. And somewhere in their synchronized spins lies a whisper from the dawn of time, a clue about how chaos gave rise to order on the grandest scales imaginable. The first stars burned bright and fast cosmic fireworks that flared into existence and vanished in a celestial blink. But did they truly disappear without a trace? Or might their remnants still lurk in the darkness, hidden in plain sight among the glitter of younger stars? The idea seems impossible after all. These ancient giants lived and died over 13 billion years ago. Yet as astronomers scour the heavens with ever sharper tools, they're uncovering tantalizing hints that some relics from the cosmic dawn might have survived to the present day. Take white dwarfs, the dense, Earth-sized cores left behind when stars like our Sun exhaust their fuel. Normally, population 3 stars were too massive to form white dwarfs. Their violent death should have left only black holes or neutron stars. But what if a fraction of these early stars weren't behemoths? Some models suggest a narrow mass window between 40 and 140 solar masses where stars could have shed their outer layers in titanic eruptions before collapsing into white dwarfs. These rare survivors would be utterly unlike modern white dwarfs, composed almost entirely of helium or hydrogen with no traces of heavier elements. Spotting them would be like finding a fossilized dinosaur bone in a city park, a primordial relic hiding among the mundane. The hunt for these ancient cinders has led astronomers to the Milky Way's halo, a sparse outer shell of stars thought to harbor some of our galaxy's oldest inhabitants. Surveys like Gaia have identified a handful of ultra-metal poor stars with bizarre chemical signatures, potential second-generation stars that might have formed from the ashes of population 3 white dwarfs. But the real prize would be finding a true first-generation remnant itself. The challenge: these white dwarfs would be fantastically dim, cooled over billions of years to temperatures barely above the cosmic background. Next-generation telescopes like the Nancy Grace Roman Space Telescope aim to spot them by their faint gravitational lensing effects, tiny distortions in starlight as they drift silently between us and distant stars. Then there's the black hole scenario. Most massive population 3 stars likely collapse directly into black holes without supernova fireworks. Unlike their stellar counterparts today, these primordial black holes would have formed in nearly empty space, with little gas to consume, and thus few telltale X-ray emissions to betray their presence. They might wander the galaxy, invisibly dark ghosts of the cosmic dawn. Yet occasionally one could reveal itself. When the LIGO Observatory detected gravitational waves from unexpectedly heavy black hole mergers, some theorists wondered, could these be the ancient remains of first stars finally colliding after eons in the dark? The Vera Rubin Observatory might soon tip the scales. By monitoring billions of stars for subtle flickers, it could catch primordial black holes passing in front of stars, a phenomenon called microlensing. Even more intriguing are hypervelocity stars, stellar runaways flung across the galaxy at insane speeds. Some might carry the scars of close encounters with ancient black holes, their trajectories hinting at unseen gravitational monsters lurking in the galactic shadows. Whether as faint white dwarfs or invisible black holes, these remnants are more than cosmic curiosities. They're time capsules from an era before planets, before chemistry, before the universe learned to make anything more complex than hydrogen and helium. Finding even one would give us a direct line to the cosmic dawn, a chance to study the ashes of the fires that first lit the darkness, and if the hunt proves fruitless, that absence would speak volumes too, forcing us to rewrite the story of how the first stars lived, died, and shaped the cosmos we call home. We've journeyed through the shadows of the cosmic dawn, unraveling 25 mysteries that defy our understanding of the universe's infancy. Each one rewrites the cosmic narrative in its own way, from the ghostly giants of population 3 stars to the paradox of supermassive black holes growing impossibly fast, from the patchwork reionization of the early universe to the eerie synchronization of galaxies spinning in silent harmony. These aren't just puzzles, they're seismic shifts in how we perceive creation itself. Consider the implications. The missing satellite galaxies challenge the very nature of dark matter. The Lyman Alpha Forest whispers secrets about the universe's first light. The anomalous radio background hums with the possibility of undiscovered physics. And the cold gas reservoirs, surviving against all odds, hint at cosmic refrigeration we can't yet explain. Every mystery peels back another layer, revealing a universe far more dynamic, far more inventive than we ever imagined. Now, standing on the precipice of discovery, we're armed with tools our predecessors could only dream of. The James Webb Space Telescope is already rewriting textbooks, capturing light from galaxies born in the universe's first chapters. Next-generation observatories like the Square Kilometre Array and the 30-meter telescope promise to push even deeper, mapping the cosmic web in radio silence and dissecting the chemistry of the first stars. Gravitational wave detectors may soon catch echoes from black holes born in the cosmic dawn itself. But this isn't just about technology, it's about perspective. Every answer we uncover forces us to confront bigger questions. What if the first stars weren't what we thought? What if dark matter interacts in ways that redefine physics? What if the universe's blueprint was drawn with rules we've yet to decipher? These mysteries remind us that we're not just observers of the cosmos, we're participants in its story, stardust trying to understand its own origins. So as you look up at the night sky, remember, you're gazing into a past still unfolding, a history still being written. The cosmic dawn isn't some distant epoch, it's the foundation of everything we are. And with each revelation, we're not just solving puzzles, we're reclaiming our place in the universe's grand narrative, one breathtaking discovery at a time. The greatest chapters, they're still being lit.